Hello everyone, Chapter 2, Lesson G, Solving Rational Equations and Inequalities. We are going to, as our objective, solve rational equations and inequalities. Wow, that's amazing, based on the fact that's exactly the title of this lesson. So, just a couple of items. We have done many problems like this prior to this lesson, so this is very much review. Okay, we did a lot of this in Chapter 1. I just want to touch on it again since we're talking about holes and vertical asymptotes, horizontal asymptotes, all that good stuff here in Chapter 2. So let's go ahead and get into the next slide, which is actually also our last slide. So let's go ahead and do that. Okay, so when solving rational equations and inequalities, the following guidelines are helpful. Write the inequality. This is based on the inequality, but we're going to work the equation in a very similar way. So write the inequality with one side equal to 0. Find the critical values, which are where the numerator equals 0 and the denominator equals 0. Finding the zeros of both of those. Use the test interval methods from polynomial inequalities to find the solution set for the original. So I'm going to start with number 1. This will be an equation, so it'll be a slightly different version than those 3 steps that we just spoke about. But I do want to take step 1 and set one side equal to 0. So I'll take 2x minus 7 over x minus 5. I'm going to subtract the 3 over and set that right side equal to 0. Okay, now in order to find critical values like I'm looking for in step 2, what I want to do is have a common denominator. So what I'm going to do is divide by 1. And in dividing by 1, I'm actually multiplying top and bottom by x minus 5. What that will do for me is get me a common denominator. So now what I'll have is 2x minus 7 minus the quantity 3 times the quantity x minus 5 over x minus 5. And we're setting that equal to 0. So let's simplify the numerator. This would be 2x minus 7 minus 3x plus 15. Okay, all of that over x minus 5. And then let's clean that up just a little bit. So that'd be 2x minus 7. Oops, I'm sorry. That would be negative x, right? 2x and negative 3x would be negative x. And negative 7 and 15 would be a positive 8 over x minus 15 equals 0. So when we're working with equations, the only difference between intervals and equations is that all we want to know is where this would equal 0. So I don't have to worry about the denominator. All I need to worry about is the numerator. So I'm going to take the numerator, which is negative x plus 8. I want to know where that would equal 0. And that would equal 0 when 8 equals x. Therefore, our solution is when 8 equals x. So let's go back and let's check that this is true. Okay, I'm plugging in an 8 wherever I see an x, and I want to show that equals, I want to show that equals 3. So that's 16 minus 7, which is 9, and 8 minus 5, which is 3. And that checks out to be 3. Okay, so that's solving a rational equation. Let's look at an inequality, which will have a slightly different third step. Okay, so step 1, we want one side to equal 0, which we have. Step 2, what we're going to do is we're going to get a common denominator. So I will take the x and multiply top and bottom by x. That gets me this common denominator right here. And I'm going to set this equal to 0 just for a moment. Actually, no, I won't. I won't do that to you. I'm going to do this, right? And then I'm going to combine like terms here. So this would be 1 minus x squared over x. I want to know where that's greater than 0. Okay, so what we do here is we find the critical values. Okay, so the critical values. And those values exist where the numerator equals 0 and where the denominator equals 0. Okay, so I see I've got one critical value at x equals 0. The other critical values, I'm going to factor this. Looks like I'm going to yield x values of 1 and x value of negative 1. So I've got critical values, okay, at negative 1, at 0, and at 1. Okay, now let's take a look real quick at what these critical values mean, okay? So where the numerator equals 0, these are going to be x-intercepts, provided that factor doesn't show up in the denominator as well. So I don't see a 1 minus x or a 1 plus x in the denominator, so those are x-intercepts. That will be where the function is equal to 0. Where the denominator equals 0 is a vertical asymptote. Therefore, I cannot have a function output there. Okay? So I want to know where the function is greater than 0. So I'm going to test around each of these values. So I'm going to test values like 2 and a half and negative a half and negative 2. When I test those values in the original function, so for example, let's test negative 2. So 1 over negative 2 minus a negative 2. Is that going to be greater than 0? Well, let's see what it equals. That's going to be negative 1/2 plus 2, which is, what would that be, 1.5 or 3/2. Okay, so if I tested negative 2, I get a positive output. Let's test negative 1/2. So that's 1 over negative 1/2 minus negative 1/2. Let's see what that equals. Well, 1 over negative 1/2 is negative 2 plus a half is going to equal negative 3/2. So when I test negative 1/2, I get a negative output. That means all values between negative 1 and 0, not including either of those, will also be negative. Okay, let's test 1/2. You might be already making predictions. Let's make a prediction. I will go with negative, just a guess. I don't know. We'll see. Actually, I'll go positive because now I'm thinking about it. Okay, 1 over a half minus a half will be the same as 1 over a half is 2 minus 1/2 is going to be 3/2, so that'll be positive. So when I test 1/2, I get a positive output. And my inkling here is that I'm going to get a negative output here, which I'm feeling like I'm pretty confident about. So 1/2 minus 2, if I plug a 2 in there, will be 1/2 minus 2, which is negative 3/2. So I picked these numbers actually very intently, knowing that I would get outputs that are similar. But notice that the graph, this inequality, would be satisfied by the following inputs. Any input that's less than negative 1, and any input that's between 0 and 1. So the solutions for this, so 1 over x minus x is greater than 0 on the interval from negative infinity up to, but not including negative 1, as well as from 0, not including 0, up to 1. All right, let's do one more example. Let's look at this one here. Looks like I already have step 1 taken care of. Everything's on one side. Notice in this case, we are going to do it less than or equal to. So what I would do in this case is I want to know in step 2 what the critical values are. So I'm going to factor the denominator. I'm going to rewrite this as negative 3x minus 12 over, factoring this would be x plus 4 x minus 3. This one you want to be careful for because the numerator in this case is not going to be yielding you an x-intercept. So let me show you why. If I factor the numerator, I'm going to take a negative 3 out. That leaves me with x plus 4. So what I get here, and you would have seen it either way, is that I'm going to get critical values at, if I set the numerator equal originally to 0, and I set the denominator equal to 0, notice what happens. I will get negative 3x is equal to positive 12, which would mean that x would equal negative 4. So you might think, oh, I have an x-intercept at x equals negative 4. Well, that's not true. The reason why is because I also have a discontinuity, right? An issue at x equals negative 4 and x equals 3. So you might think, oh, I've got a vertical asymptote at both of these. Well, you have a vertical asymptote at x equals 3, but because this shows up, this factor shows up in numerator and denominator, that's actually a whole. Okay, that's going to be a whole. So let's do a little sign diagram here at negative 4 and at a positive 3. Okay, both of these, this would be a whole, which I could represent that way. This would be a vertical asymptote. So these do not have possible outputs for an input of negative 4 or positive 3. So we're going to test some values. Let's test 0. That's a nice one. We'll test positive 4. We'll test negative 5. All right, so let's test a negative 5 in each. So that would be negative 3 times negative 5 minus 12 over negative 5 squared plus negative 5 minus 12, which will equal, that'll be 15 minus 12, which is 3, over 25 minus 17, which is 8. So that's going to be a positive. So I'm going to get positive outputs when x equals negative 5. Okay, let's test 0, which should be real nice. If I were to plug in a 0, I would get, let's see here, where are you? There you are. If I plugged in a 0 in for all of the x values, I'd get negative 12 over negative 12, which would be a positive 1. Okay, so when x equals 0, then we get output of positive 1. So it's positive on both of those intervals. That's interesting. Okay, so let's plug in a 4. I'll use, we'll go red. Let's plug in a 4. So negative 3 times negative 4 minus 12 over negative 4 squared plus negative 4 minus 12. Okay. Let's see what we get here. Whoops, sorry. That should be a positive 4. So that would be equal to negative 24 over 16 plus 4, which is 20, minus 12, which is 8. So it looks like I get a negative 3. Okay, so my output here at 4 is negative. Okay, so let's look back at the original. The original question is asking us, where is this expression less than or equal to 0? Well, we don't have any x-intercepts. There are no values where it equals 0, so we don't have to worry about that, right? Because the only two places that it could have happened had a whole and had a vertical asymptote. Therefore, the function is less than 0 Right, this function negative 3x minus 12 over x squared plus x minus 12 is less than or equal to 0 on the interval from 3 to infinity. Pretty good problem. Yeah, go ahead and shoot me any questions you got with inequalities or equations of rational functions. All right, guys, we'll see you in the next video.